Hello and welcome back to Fundamentals 1. Our lecture today is going to be focused on sources, specifically electrical sources. You can basically view sources as anything that excites a circuit, anything that provides a signal to a circuit. And starting in this course, we're going to view sources primarily in the area of providing a voltage or a current to a circuit. Now, there are really many different ways you can think about sources. This particular table here gives one taxonomy that we're going to be using in this class to essentially understand different types of voltages and currents and different types of ideal or non-ideal conditions. So let's go here line by line to give you a little bit of a viewpoint of what we will be talking about. So first of all, let's focus on the type of a source. There are essentially two different types we'll be talking about. There is a source that can give us a voltage or a source that can give us a current. And each one of them has advantages and drawbacks. Specifically, we will be talking about them when we talk about different applications. So for right now, just simply consider them to be practically equivalent. Another part that we will worry about is about the value of the source. Are we talking about an independent or a dependent source? Then we will be worried about whether the source is ideal. For example, we could have sources that give us all the characteristics in real life that we want, or we can have sources that some of those characteristics are undesirable. For example, they may decay over time. Then there is the issue of time dependence. Are we talking about a source that gives us a constant signal? We will call that, for example, a direct current source or a DC source. Are we talking about sources that are variable with time? One particularly important time dependence is a sinusoidal source, or later on in this class, we will be talking about AC, alternating current sources. Then we also have to worry about how do we connect sources together? When do we connect them? What are we trying to achieve with that? And are we allowed to put those sources in series, or are we allowed to put them in parallel? And finally, even though we do use sources to excite circuits, sometimes we need to turn them off. And so the question is, how do we turn a voltage source off, and how do we turn a current source off? So in this particular video, I'm going to focus on the first four parts, and then there are other videos that will give you essentially the connecting properties and the turning off properties. So first of all, I would like to start by talking about the independent sources. So an independent source is essentially a source whose value is independent of the circuit that is connected to. So let me write this here. So the value of the source is independent of the circuit that you're connecting this to. So in other words, the source will behave in exactly the same way in circuit A or in circuit B. It will work in exactly the same way if you use it, for example, to power a watch, or if you use it to power a vehicle. Now, we have independent sources that may be voltage sources. This is an example of a voltage source here, or it can be a current source. And notice the symbols. We have actually used those symbols before. A voltage source is typically indicated by V, which is basically the value of the voltage and the polarity. And this voltage source will have a plus or minus, meaning that one side, one node, is sitting at a higher voltage than the other, and the potential difference between those 2 points is V. On the other hand, a current source is indicated by I. This is the value of the current, and is also indicated by the arrow here. And this is the arrow that signifies the direction of the current that this source will impose on the circuit. I do understand that most of you are probably familiar with some type of a voltage source. For example, many of you have used batteries, but may not necessarily be as familiar with a current source. The reality is that most of you probably have not walked into a store and asked to buy a current source. However, for right now, please do accept that they are equivalent, and not only that, but they're also equally useful. And there are certain techniques that we use to build each one of these type of sources. Later on, we'll discuss towards the end of the class of how we can actually use other devices that are unknown to you as of right now to build current sources. Independent sources may also be variable in time. For example, an AC, a sinusoidal source, which may either provide a V or an I, a voltage or a current, it can actually be very useful in real-life scenarios. Notice here that I use capital V and capital I, while on the third source here, I use little v and little I. In general, we use capital letters to signify DC sources, meaning constant sources, sources that don't change with time, and we use the little letters V and I to signifying time variable sources. The same thing is true for any other symbol you'll see in this class. For example, a V or an I, it might be voltage drop across a resistor, or it could be a current through a diode later on. So keep in mind that capital letters normally mean DC or constant numbers, while V and I mean time dependence. Also, even though the AC is a very common, I would say, source, there are other type of time-varying sources. For example, you might have a square, or you might have a saw-shaped source. Now, there's one type of source that is incredibly common, and these are the batteries. So the batteries, they basically have their own symbols, as they can be seen in those slides. So the most common symbol is the one that you will see here to the left. It's basically a V with plus or minus, where the long bar is the plus side and the short bar is the negative side. And sometimes when people want to indicate whether something has a single cell or maybe 2 cells or 3 cells, they will use symbols like this. In this class, I will actually try to avoid those symbols, and any battery essentially will be represented by the very first symbol that you see right here. Now, let's change gears a little bit and talk about dependent sources. So unlike independent sources, whose values are practically independent of the circuits you connect them to, dependent sources do have a value that actually depends on some other value in the circuit. So I'm going to write here that dependent sources have values that are dependent on something else. So that something else may be a voltage or a current, but it basically sits somewhere else in the circuit. Now, dependent sources, unlike the circles that we're using for the independent ones, are primarily signified by the diamond symbol. So the diamond symbol that you will see here or here is the symbol that we're using to indicate the dependent source. Now, a dependent source may again be a voltage source. For example, look at this V1 here. It actually signifies a dependent source, or a dependent voltage source, or it can actually be a current source. This I1 here signifies a dependent current source. Notice that except for that diamond symbol, everything else remains the same. I still have a plus or minus polarity for the dependent voltage source, and I still have an arrow for the dependent current source. Now, if you check those values, let's say, for example, the V1 or I1, you will find out that they depend on something else. For example, for the dependent voltage source, you will find here that there is this V, where this V is the voltage drop across this device. So that basically means that if you double V, if you double the voltage source across that device, the voltage drop across this device, then V1 also doubles. Similarly, if you check this current source here, I1, its value depends on this current I, where the current I is shown right here. So again, if you make I double, you will also double I1. Notice that in both cases there is a number that multiplies that. For example, here the number is alpha, while here the number is x. Now you may say, okay, this seems a little bit weird. First of all, I've actually never bought a diamond source. Second, why on earth would you ever want these things to depend on something else? Let me answer the first question first. Yes, indeed, you will never go to a store and buy something that looks like a diamond and they will tell you this is a dependent source. That's not how it works. These are just symbols. What is actually hidden behind that, there could be a bunch of different technologies that implement the dependency you see right here. They could be using diodes, they could be using transistors, they could be using more complicated electronics, some of which we will actually see in this class, some of which you will have to take more advanced courses to understand. But the point is that this is just a symbol. It's just a model. We don't sell them like this. The second question, which was, why on earth would you like to make sure that something depends on something else, is because that's a lot of usefulness. There's a lot of usefulness in that. For example, let's suppose that you had to make a sensor. And let's suppose that the sensing device was right here. And that sensor, for example, could be a temperature, could be humidity, could be strain, could be pressure, could be speed, could be any sensor you like. Well, you would like to read that sensor and then generate an electrical signal that is proportional to that reading. For example, you would like to make sure that you measure maybe the pH of a solution or the speed of an aircraft, and you would like to make sure that you transfer this to the electrical domain. And so anytime you sense, for example, twice the speed, you double your voltage. That's exactly what this guy will be doing. So a dependent source is not only something useful, but it is something very practical in a very, very diverse range of applications. Similarly, you might say, well, I don't want my signal to be generating a voltage. I want my signal to be generating a current, in which case you might be choosing to make a dependent current source. Now, in the examples I've shown you so far, I've actually focused on having a voltage V1 here, depend on another voltage V, or a current I1 depend on another current I. It doesn't have to be that way. It's totally possible to have a source, like the source V2 I'm showing here, that actually depends on a current I. The I, by the way, is right here. So it's totally possible to generate a dependent voltage source whose value actually depends on the current. Equivalently, you can generate a current source, I2, whose value actually depends on another voltage V. So essentially, all possible combinations are possible. So, and we give names to those things. For example, we call this very first source here voltage-controlled voltage source. So voltage-controlled VC, it signifies that this source is controlled by a voltage. Vs, the voltage source, signifies that this is providing a voltage to you. Or it could be this source here is a current-controlled current source, CCCS. And there are all different combinations. For example, this source here is a current-controlled voltage source, CCVS. And finally, this one here is a voltage-controlled current source, or VCCS. So all different combinations are here, and all different names are here. So once again, dependent sources, even though you may not have seen them before, are equally useful, equally good sources as the independent ones. The only difference is that the values of those sources depend on something else. But other than that, they behave and you deal with them like sources. Now, I want to show you some common diagrams that you might encounter in terms of using dependent and independent sources. Let's focus for right now the diagram on the left. So this is a diagram where you will see many times in more advanced courses, and it has one thing that sometimes is a little confusing, and I just want you to pay attention to it. There is, of course, a nice independent source here. There is a nice dependent source here. There are two devices that you can clearly see here. But then there is this line that seems to be connecting two otherwise different circuits. And so what is the impact of this line, and how should you understand that? So the first thing I would like to say is that the impact of this line is absolutely zero, in the sense that there is basically zero voltage that will flow through it. Why? Because zero current. And why is that? Is because currents like to flow in closed loops. And so what happens here is that you clearly have an open loop. There is no closed loop here. And so that current that will basically flow through this line is exactly zero. Now you might say, well, if that's the case, if the current through this wire is zero, is it okay to omit it and draw exactly the same circuit as I did on the right without this line? Well, the answer is absolutely yes. You can omit it. There is absolutely no difference between the left circuit and the right circuit with and without a line. But if that's the case, you may ask, then why do we draw it? Why will sometimes I see it and sometimes I will not? So this is honestly a matter of preference. So some people will draw this line simply because they want to indicate to you that the ground that you see on the left part of the circuit and the right part of the circuit are basically the same. So it's kind of a reminder that there is a common ground between the two circuits. Others will actually draw this line so they have a physical reminder that those circuits are actually physically connected to each other. They don't have to be. For example, the circuits on the right without a line, you really would have no clue how far away physically they are at. Maybe one circuit is on Mars and the other circuit is on the Earth, and the signal we get from the circuit on Mars simply is influencing another signal we're reading here. Now, when somebody is drawing the circuit here to my left, because of the existence of that line there, is a pretty good indication that most likely those circuits are physically close to each other and might even be in the same box, for example. So I'm saying all of those things to explain why sometimes we draw those lines that have zero electrical importance and sometimes we don't. What you should really keep on that is that if you see a circuit with this type of a line down here, you can safely ignore it. It has really no influence. Now, I mentioned before that dependent sources can basically model some very interesting effects. So let me give you a couple of applications where this is the case. So first, let me focus here to my left. What you will basically see there is a wireless charging station. The wireless charging station is right here, which is on the ground. And then whenever you go and park a vehicle over that, an electrical vehicle, then essentially you will transfer power wirelessly from the charging station to the vehicle, and you will basically charge the car. So as far as the car is concerned, essentially you have a dependent source. There is a dependent source inside the car that is basically charging the car, and that dependent source depends on how much power you have on the wireless charging mat, and also how far away is this vehicle from the wireless charging mat. If the vehicle is too far away, the source will simply be turned off. And so clearly, the dependent source inside the car, let's say for simplicity that is a voltage source, will actually depend on some distance and some power, right? The distance is the distance between the vehicle and the charging mat, and the power is the amount of power that you're basically feeding the charging mat with. So this is a really good example of understanding how we model a real-life situation, a wireless charging situation, through a dependent source, which would represent of what's happening inside the vehicle. Another example that I'm having here to my right is essentially a piezoelectric source. So it turns out that if you vibrate a magnet, the magnet is shown right here, within a coil, the coil is shown right here, then you will basically generate power. This is a law of physics which you may have seen in basic physics courses. I'm not going to spend time here analyzing that, but indeed, if you physically vibrate this magnet up and down, and then you will actually change the magnetic flux through this coil, and because you're changing the magnetic flux, you will generate a voltage here, and you can use this voltage to power, for example, sensors. This is a circuit and an example that we built in my own group. This is a student who is basically wearing this device, and as the student is walking, this device is basically generating power. This power could be very useful, for example, for wearable electronics or for wearable sensors, and it's a completely battery-free system. You're using your own vibrations, your own walking pattern to basically power these devices. So if, let's say, you were powering maybe a wearable sensor here, the source of that wearable sensor could be modeled as a dependent source. So that source, let's say, for example, is a voltage V, would basically depend on how fast you're walking. So it's basically the walking speed. It would depend on how heavy is the magnet, so maybe the mass of the magnet. It would depend on how big is the coil, and maybe a few other parameters that I'm omitting here for simplicity. But my point is that this is another example of a dependent source that is a very practical example, and we'll be using the dependent source model to study the influence of that in this class. Now, finally, let me talk about the issue of ideal versus non-ideal sources. So when we talk about ideal sources, essentially we have to think about two main things: the value and the power of the source. So the value of an ideal source is essentially independent of time. So that means that when you build the source, and 100 years from now, the source will work exactly the same way. So ideally, if you were to buy a battery today and you were to use it 20 years from now, you would find the same voltage across the battery. Of course, we know that this is not true, and all sources eventually do decay, but that would have been a characteristic of an ideal source. The second characteristic of an ideal source is that it can provide any power you like. So the power, I'm going to write here, is whatever is requested. So if you, for example, if you had an ideal voltage source, you could connect this ideal voltage source to power a wearable watch, or to power a vehicle, or to power the entire state of Indiana. That ideal voltage source should be able to do all three of them because it could provide power for all three of them. In reality, that's not true. Of course, we know that you need a different type of a power source to turn a watch on and a different type of power source to power all households and industries in Indiana. Now, the way we view that in the symbols we're using here for the sources is the following. If you have a voltage source, then you definitely know the voltage drop across its terminals. So, for example, somebody may say, here's a 5-volt battery. But if you ask this person exactly how much current will flow through my battery, the answer is, well, it depends. It depends. If you connect a little device here that draws maybe 1 watt of power, then you're going to draw 1 amp. Actually, 1/5 of an amp. However, if you connect here the entire state of Indiana, and this is not an accurate map, then clearly you're going to basically draw as much current as needed to power everything in the state. That would be an ideal voltage source. An ideal voltage source will have a constant voltage no matter what. No matter what you connect to it, the voltage is always 5 volts, but the current will basically depend on whatever is requested by the load. Let me say exactly the same things in an analogous way for the current source. The current source will do everything in its power to give you the current I. If you buy a 1 amp or if you build a 1 amp current source, you're guaranteed, as long as the source is ideal, to have 1 amp current flow. But what the voltage will be across the terminals, what the voltage drop will be across the terminals, will actually depend on what you connect to it. It will be such that the V times I, the provided power by the source, the delivered power by the source, must match whatever the load requests. So if the load requests 1 watt or 1,000 watts, you will change voltage accordingly such that you get the requested power. So these are the two main characteristics of ideal sources, and as far as this course is concerned, we're always using ideal sources. The voltage or current will be always what is signified by the source, but the power will be whatever the load is requested. So thank you very much for watching this video, and I hope you have now a better understanding of sources. We'll see you next time. Thanks.